All right, we're going to draw the free body diagrams for these various situations just to kind of review some of the stuff we covered in class. And one of the most important things around Newton's laws is that whenever you have movement with an object, that movement is not, like we don't draw any kind of arrow in a free body diagram for the fact that it's moving. So when an object lies motionless, there is a reaction normal force from the floor, and there is its weight. Moving at constant speed without friction, there's a normal reaction force, and there is its force of gravity, the weight on it, because the Earth is pulling on it. This fact that it's moving at constant speed does not make it into the free body diagram. And then here, with this object slowing to kinetic friction, we don't draw any arrow for the slowing down. There is a friction force going to the left against the motion. And the way we can tell it's slowing down is, well, we have to read the wording, but the way we know that there's a force to the left is we actually see evidence in the free body diagram of this unknown force pointing to the left. And that's how we do our calculation. Now, here the object slides without friction. Here the normal force needs to be perpendicular to the surface. So that reaction force goes diagonally like that. And then there's the weight pointing down. Here, static friction does prevent sliding, so we do need to be careful to label all our forces carefully. So we will have, again, this normal reaction force pointing upwards. We have the weight of the object pointing down. And then the friction force actually opposes the motion down the inclined plane. Whoops. So I should actually draw that a little bit more carefully. So this is the weight force going down, the normal reaction force pointing, and then we're going to have this friction force opposing the motion pointing this way. Now here we have an object suspended from the ceiling. So we have its weight, and we have this tension force pointing up, supporting it. So because it's not on the surface, we don't have any normal contact force. Next, we moved on to take a look at problem number 2, and we want the free body diagram. Now notice, the 30 Newton force is bigger than the 10 Newton force, so the box wants to move to the right. These are just given forces. It says the box is pulled with 2 ropes as shown below. So this is supposed to be rope number 1 and rope number 2 here. We draw the free body diagram, and we're saying that there is an extra friction force also acting. So we have the normal reaction force, we have the weight, we have F1, we have F2, and in addition there is also a friction force. Now, we're saying we're pulling with the maximum force needed just before the object moves, and we want to know how much friction is acting on the box. So let's be really careful here. When we set up our equation, just to be clear, we're talking about the x direction force. This is the thing that we said in class, is that when force is balanced, the forces add to 0. And when forces don't balance, that unbalanced force makes the mass accelerate. In this case, we have totally balanced forces. So in the x direction, we see that we have F1 minus F2 minus F. The F1 points to the right, and the other 2 forces point to the left, so that's why they're subtracted. And then in the y direction, we have the normal reaction force pointing up. We have the weight pointing down, and they cancel vertically, again, because we have no vertical movement either. Now to actually solve this question, let's just plug in numbers. So I have 30 minus 10 minus F equals 0. So I can actually obtain the friction force just from this math here, and I get a 20 Newton friction force acting on the block. Now assume we get the block moving and the friction acting on it needed to keep it moving at constant velocity is 10 newtons. We want to know what F1 is equal to. So again, we're still going to have F1 minus F2 minus F equals 0. And what we're saying here is F is 10, F2 is 10. So F1 minus 10 equals 0. And that gives us an F1 equal to 20 newtons to keep it moving at constant velocity. Remember, when we're moving at constant velocity, forces are balanced, so we don't need to write MA there. So constant velocity does, in fact, imply balanced forces. Now let's look at a situation where the forces are not balanced. So we have, from the free body diagram, F1 pointing to the right, minus F2 to the left, minus F to the left, and the effect is that the mass accelerates. And we are told that the mass of the object is 10 kilograms. So we plug in 30 minus 10 equals 10 times A. That gives us 10 equals 10A, and so when we isolate A, we're going to get that A is 1 meters per second squared. Next, we're moving on to this thing here. Now, we're going to actually solve these in class on Wednesday, but just so you know, the free body diagram in this situation, we're going to have a normal reaction force, we're going to have the weight pointing down, and then we actually have this angled tension force, and if we like, we can fill in the 30-degree angle here. And then for the very last problem, we're going to solve again on Wednesday, but just to set up the free body diagram, for A, we're going to have a tension going up, and then we have the weight of A pointing down. Similarly for B, tension going up, and the weight of B pointing down. So that's the homework that's actually due for Wednesday when I see you next.